Next topic, finding torque on a current carrying conductor. So here I have a north pole, south pole, and here is a current carrying loop. Okay, it's a current carrying conductor loop. We're making it as a coil. Here, these are the brushes. Okay, that's a brush, and we call this as slip ring or commutator. In DC we call it as a commutator, in AC it's called slip ring. Both of them are same. So basically this is a DC because it's a DC source current. So current I is passing through this, current is entering in this, and current is going out here, and there is always magnetic field between north and south pole. So if I draw this in a diagram, we're trying to find what is the force on this loop of that on this loop because of the magnetic field. So here is a magnetic field B, north pole, south pole, magnetic field B. Now current is entering in this conductor, current is coming out in this conductor. Now I'm going to take the length of this conductor as A. So this length, I'm going to take this length as A. Okay, and this width as B. Okay, width of that conductor is B and length of this conductor is A. So the total area of the loop is A times B. So area of the loop equal to A times B, AB. Now I'm going to take this conductor 1, this is conductor 2, this is conductor 3, and this is conductor 4. Okay, so there are 4 conductors. I'm considering that as a whole conductor. Okay, now the pivot point is somewhere in the middle. Okay, so this distance, I'm going to take this as, this distance is B by 2. Okay, B by 2, because the total distance is B. Now whatever this distance, I'm going to take this as B by 2. Now the force on conductor 1, because of the current carrying conductor, I'm going to take F1 equal to force on conductor 1 equal to, there is a magnetic field I and length of the conductor BIL sin theta. Okay, theta is angle between the I and B. Okay, so when in this case they're perpendicular to each other, so theta is 90 degrees, and the length of the conductor, I'm choosing that as A, so F equal to BIA. Theta, I'm going to leave it there because theta value is going to change when it is moving its direction. Okay, so but force on the conductor 1, which direction? Okay, by using the right hand rule. If you use the right hand rule, so thumb indicates the force direction, middle finger indicates the magnetic field direction, and then forefinger indicates the current flow direction. If you use that form, if you use the right hand rule in the direction, the conductor 1 is going to move towards down. Okay, conductor 1 is going to go down, towards down. Now force on conductor 3, F3, force on conductor 3 equal to same thing BIA, but it's going to be upward because current in conductor 3 is coming towards down. Here current is going up, so that's the reason they both are going to go in opposite direction. Now force on conductor 2. Now if you look at F2 equal to BI, length is nothing but, total length is nothing but B. Okay, sin theta, where theta is angle between B and I. What is the angle between B and I in this case? In this case, theta equal to 0, so this value equal to, so F2 equal to 0. Angle between magnetic field and current, in this case, see, magnetic field is in this direction B and current is also going in the same direction I, so the force acting on this conductor is equal to 0. Now we are trying to find the torque. Torque is nothing but torque equal to force times distance. What is the distance we need to take? The distance is from the pivot point, so here is the pivot point, to this end conductor, so that's called distance. So if you look at the total torque on that conductor, tau equal to F1 times B by 2 plus F2 times B by 2. Okay, because one is going towards down, another one is going towards up, so they both are going to add up together. Okay, we know F1, sorry, this is F3, my apology, this is F3. So now F1 and F3, they both have the same magnitude. Okay, so it's BIA times B by 2 plus B by 2, it's B, so BIA times B, A times B is nothing but area of the loop, so tau equal to BIA sine theta. Okay, still I have that sine theta there, so it's going to continue here. This is for one loop. If there are n number of loops, then the torque on that conductor tau equal to n times BIA sine theta. Okay, so this is the torque formula. So this is how an electric motor is going to work. If you place a current carrying conductor in a magnetic field, it will experience a force. Now if you place a current carrying loop in a magnetic field, it will experience a rotational force. Rotational force is nothing but torque. Thank you.